you can use the MATLAB to calculate. First, you get a whole row of 0. That makes sure the rank is less or equal than 4. And if you do a little bit of Gauss elimination, you can get another row of zeros. And in this case, the rank of A is really equal 3. If you equal 3, what's the problem? And then your eigenspace, this eigenspace, we call it, let me see how I write down the eigenspace. V, yeah. The V of the X A, it really equals 2. You have 2 freedom. 2 freedom. And remember from the last few lessons, if you have 2 freedom, you remember we get 1S, 1T, you don't get a straight line. Now you get a plane, right? So how many vectors you can find on the plane? Even you get a unit vector, a plane, you get infinite many vectors. So the problem is your dimension. The DIM means the dimension of the eigenspace. That means the solution of X is 2-dimensional. That is a problem. Let me give an example what's wrong with that. If your dimension is 2, let's say you got a 2-vector solution, 0, 1/2, 1/2, 0. And another one is 1, 0, 0, 1/3, 1/3, 1/3. You got these 2 solutions. Now you have this is X and this is Y, and those are the vector to make it the solution plane. Any combination of the X plus Y will be a solution. That's what I call a plane. You can make it as 1/4 of the X, 1/4 of the X, plus 3/4 of Y, and then you get another solution. And this solution could be any number on the plane made by this X and Y. So you cannot find the unique ranking. Then it's useless for that ranking system. So we definitely need to fix that problem of the dimension equal 1. Again, we can do a little brainstorm. How do we fix? A simple idea is to first fix this disconnect and the dangling node. And what you do is you just mercifully give a little bit of vote, equal spread among all these sites or web pages. You give a little bit. How little is good enough? Just don't make it all 0. The problem is this all 0, right? Just don't make it all 0. And you just say, let you get a little bit to him. Let's get 5%. How about that? You get 95%, 5% to here. And then you only give 95% to that guy, give 5% to here. And you only give 95 to that, give 5%. Everybody spare a little bit proportionally to the dangling part. And that solves 2 problems. First, you don't get the dangling node and also connect the subweb. That solves all the problem. So once you get this idea straight, you just need to write the math. The mathematics is this. Okay, here you go. I create a matrix S. The S is a uniform matrix. If it's a 4 to 4, just get it to 1/4, 1/4, 1/4 here, 1/4 here. It's a uniform matrix. Give everybody a little bit the same. And then I got this modified matrix M equals 1 minus little m to the A. A is my original matrix of the internet structure. That's my A. And this is my A. And then I'm going to add the S with a little weight. M is our choice. If you choose M equals 0, what you get is the A, right? Nothing. If you let the M equal 1, there's no A left. There's all S. So the S is simpler. If I have 4 pages, so 1/4, 1/4, 1/4 everywhere. And you see it's a stochastic matrix and even distributed. It depends how do you choose the M. And the moment ago I said that you give, just like in this welfare system, you give mercifully a little bit, but you don't give too much to the poorest guy become richer than the other people. Just who is the poorest guy? Is this dingling note, right? You got all the zeros here. Just give a little bit. How little is good enough? Just make it not 0, but don't make it promoted bigger than the other one. Just make it still the poorest one, but it's not going to be 0. That's the principle. So by practice, and if you look at average, maybe have 5, 6, 4, average 5 to 6 of links. And then the best choice of this number is this, 0.15. That's statistically figured out. And once you get this, you fix the problem. So according to the example 1, I looked the 4 pages, you remember? This is the matrix. And this is the original solution. But now what I do is this. I make this A times 0.85, that is most of the A, plus 0.15 of this S. What is the S? Or 1/4. 1/4. Just put 1/4 everywhere. Because it's 4 pages, right? This is a uniform page. It's overlap another 4 pages. What are the other 4 pages? It's like this. All connected. Are you with me? That's how you get this page. And then you overlap this to the old structure, put the most weight, 85% to the original one, a little influence to the second one. Now your dual system, we're going to make this a little bit different. That matrix is not the previous one. It's different. The solution will be this. It's different in some sense, but will not affect the ranking. That's all we care, right? We don't care those numbers. You remember the first one is the first, the third one is the second. You see, still this is the first, this is the second, the fourth one is the third, and this is the fourth. And then this is the third, this is the fourth. See, this change the numerical result, but that's not change the ranking. That's good. Or next, come back to the old one, fix the problem. This 5 page, have the dangling node, and the disconnect the subside. You cannot rank in. Now, intuitively, why you cannot ranking? Let's say in United States you have hundreds of millions of websites. In some country like North Korea, you have another thousands of pages. Of course, the thousands of pages, if they're disconnected completely, it got more weight if you do the same calculation because you divide less. And this you have shared weight with millions of pages. Of course, you're going to get small score. What I'm saying is if you have a disconnected system, there's no common reference. If you don't connect, have no common reference, you don't know which one is really more important. That's why we have multi-solutions. But now, when you overlap a little bit, and then you connect it, once you connect it, you use the same reference, you get the unique solution. So that's the original matrix. Because the ranking of this is 3, and the freedom is 2, you got this dimension of the space bigger than 1, no unique solution. But now, look, when I start the M basically is 85% of A plus 15% of the S, which is 5. S is this, 1/5. 1/5 is everywhere. And then you get this matrix. Well, you observe, this is not a 0, right? It's 0.03, it's not a 0. And you have a unique solution. What's the solution? You know, this is the first, tied at the second, this is always the last. Doesn't matter. You got a unique solution. That's what matters. Okay, we solved the problem by just modify the system a little bit. Finally, in real world, we are not going to have 4 pages, 400 pages. We have 4,000, 400,000 pages. What are we going to do? Are we going to solve this equation? No way. We don't do that way. Again, we do the so-called iterating computation. You learned this when we discussed the Lesson matrix. How do we find the eigenvalue, eigenvector there? We just start from any guess. Initial conditions do not matter. If you do enough time, each time you get this xk equals the A times the x0 of k times. You are going to eventually converge to the eigenvector and the eigenvalue. So you only pick up any initial condition and keep multiply the m. They either exploded if the lambda is bigger than 1 or decaying to 0, you found the eigenvalue. And we did that in the Lesson matrix. The only thing different from the Lesson matrix is we do a division, we call it normalization. The normalization is always keep the vector xk be a unit vector. In that way, they don't let a few number dominate. So the same idea as you calculate Lesson matrix, we are going to find the solution practically by just doing it thousands of times of the multiplication of the matrix. All right, this we finished today, the last lesson of our first module. We're going to have 1 week of break, and we'll come back to the next module, optimization. Everything we built up on matrix. The language for the next 2 modules are all matrix. Keep that in mind. We are pretty much fill the gap of the course at this stage. See you in next time.